So in the last video, we saw how to find the electric field of a point charge using Gauss's law, right? And in this video, we want to do a few more sophisticated examples, right? And we're going to bring back the ideas of charge density as we do so. Okay, we're going to bring back the ideas of charge density as we do so. So first things first, let's look at the electric field of a line. Now, there's one more caveat with Gauss's law that I didn't explicitly mention in the last video. I did mention that we can only analytically calculate Gauss's law with closed equations and nice, formal calculations in highly symmetric cases. When you have things like lines or cylinders, technically you can only use Gauss's law if those objects are infinite. Now, you can get approximate calculations using Gauss's law if the objects are finite, if you're very, very close to the surface of those objects, and or you look at small enough sections so that the objects essentially look infinite, right? But you technically do need to have those in order for Gauss's law to hold universally for those particular cases. So one such case would be a straight line. So imagine this is a uniformly charged wire. Okay, imagine that this is a uniformly charged wire. And uniformly charged wire is going to have charge density of lambda. Okay, it's going to have a charge density of lambda. And what we want to do is we want to find what the electric field of this wire is. Now, once again, we know from the integral calculation what the electric field for this ought to behave like. Okay, even if you haven't explicitly done that calculation, I invite you to set up a calculation for an infinite wire. Imagine this keeps going infinitely long in this direction, and it keeps going infinitely long in this direction. And use this equation to find the electric field of this wire at some point above the axis, some point P. And what you'll find is that the field is proportional, not to, it doesn't behave as an inverse square law, but it behaves as an inverse law. It's proportional to 1 over the distance, not 1 over the distance squared. Okay, so this is the behavior that we want to predict, right? Or that we want to replicate using Gauss's law. Now, this is a thin wire, okay? This is a thin wire. So what kind of symmetry is going to be the appropriate symmetry for this? Well, if I want to enclose this with a Gaussian surface, the natural thing to do is going to be to enclose it with a cylinder and let the cylinder have its central axis along the wire. Okay, so I'm also going to let my cylinder have a radius r. Okay, now remember that lambda is equal to dq over dx. So if I look at some chunk of my wire with width dx, and it contains charge dq, then lambda is equal to dq over dx, and therefore dq is equal to lambda dx. Okay? Now, if my Gaussian surface has a length L, okay, then there's some geometry we need to talk about the Gaussian surface here in just a moment, but I want to understand how much charge is enclosed on this line, because I need to get Q enclosed. So using this kind of idea, if I move away from the idea of differential elements and differential lengths and look at this total length L that stretches from here to here, then how much charge is on that line? Well, if this is a uniformly charged line, then Q enclosed is just going to be equal to lambda times L. Okay? Q enclosed is just going to equal lambda times L. And so now I've already got part of my calculation, right? So we'll go ahead and just write it down. E dot dA is going to equal Q enclosed over epsilon naught, but we've already said that Q enclosed is equal to lambda times L. And so, with that in mind, it's now time to talk about our dA. And first, we also have to justify why we can pull E out of the integral. If this is a uniformly charged line, okay, if this is a uniformly charged line, then the line is in 3 dimensions, but in the easiest dimensions to visualize for us are going to be in the plus y and minus y directions. The electric field lines are going to be uniform, coming off of the wire like this, and down like this, right? And so since these are going to be uniform, they're going to pierce the surface with the same strength all along this length. They're going to pierce the surface all along this length. And you'll notice that the actual edge, or this face of our Gaussian surface, is not going to contribute anything, because the surface of my cylinder at these points also has a normal vector, that's terrible, has a normal vector this way, but the surface here has a normal vector this way. And same thing for the back surface back here. It will have a normal vector this way. And so since the electric field is uniformly outward from the wire, not along the wire, none of the components of the electric field are going to be along the wire, then the two sides, the two faces, aren't going to contribute anything. It's only going to be the body of the cylinder that contributes. Okay. But because the wire is along the axis of the cylinder, the electric field will have the same value everywhere along the surface here and the surface here. And as a result, we can pull E out of the integral. Okay, so what is going to be the dA? So if I have a cylinder, and I'm going to lay mine like this. Okay, if I have a cylinder, what is the surface area of the body of that cylinder. Well, imagine slicing that cylinder. So imagine like a wrapping paper tube or a paper towel tube or a toilet paper tube, and you slice it right straight down like this. And then you unfold it into a rectangle. This is the surface area of the tube. Right? This is the surface area of your Gaussian surface. And what is that surface area? Well, this length is going to be L. And the distance around the circumference, when unfolded, is going to be this distance here. So this is the difference of the circumference. Okay? So if my radius is 2 pi r, then the circumference is going to be, if my radius is r, then the circumference is going to be 2 pi r. And my surface area then is going to be that distance multiplied by my length, because my area is length times width. So the area is going to be 2 pi r L. So this is going to become 2 pi r L. Okay, and the L's cancel, and our grand result is that E is equal to lambda over 2 pi epsilon naught r. And sure enough, we recover the fact that our field should be inversely proportional to the distance away from the wire, not the distance squared. So this is probably the second most general result of Gauss's law. Okay, the simplest application is the point charge. This is one of the most useful. It might not be the second most useful, but it's definitely up there. We'll talk about the plane, and then we'll address the a plane of charge, an infinite sheet of charge, and then we'll address the uniformly charged sphere. Okay. So imagine that I have an infinite sheet and this infinite sheet contains uniform charge density sigma. Okay, so it has uniform charge smeared all around it. I want to know what the electric field is for this sheet. Okay. And so what we do is we say, okay, I'm going to look at because what does the electric field look like? If this is positive sigma, then the electric field is pointing away from the sheet, and it's uniform all over the sheet. And I'm not going to spend 15 minutes drawing all of these vectors, but these are coming up off of the sheet like this, right? And they're uniform, and so on. So what I want to do, or what I would do, what kind of surface can I draw that would capture flux that looked like this, right? So I will draw some field lines in the middle of the sheet here. To serve as my example. And the shape that I use is going to be a cylinder. So I draw a cylinder that is basically captures the field lines and extends down to the face of the sheet, right? And so now I have a surface area that these field lines are piercing, right? So these field lines, they're going to diminish in strength, but their direction is still going to be this way. So they're still going to pierce this surface, right? So these field lines are piercing the face here, and that face has surface area A, right? And if the sheet is uniformly charged, then the field lines are all straight up. They're all the same strength at the same height above the sheet. And so that is the justification for the E field at the boundary of this face being constant. So then that allows me to pull E out of the integral. So now we've already made progress. But now what charge is enclosed? What is Q enclosed? Well, remember sigma, surface charge, is equal to charge per unit area. So if I know what the area is of my cylinder, what the faces are, then that is the same as this area A. And my Q enclosed, the total amount of charge I enclose, is going to be equal to the area of my Gaussian cylinder times the charge density that I've put on the sheet. And so now I have E integral dA is equal to sigma A over epsilon naught. And the integral of my surface area element is just going to turn out to be the total area. So this is still just A. And so my A's cancel out. Okay? But there's one more subtle thing. Okay? There's one more subtle thing. This is for the top half of the sheet. If this is truly an infinitely thin sheet, then there's field lines coming from the bottom of the sheet too. And those have some flux. So if I let this cylinder extend through the sheet so that if I drew my sheet completely edge on, then I would have field lines that went like this. And I would have my cylinders. One cylinder would be here, and the other cylinder would be here. And so they're both capturing the same amount of flux. But it's the same charge density and the same area of the surface you're looking at. Okay? So what that tells us is that this is for the total sheet. Okay, this is for the total sheet. When you only look at the top or bottom, if I only look at the top or bottom, then I'm capturing half of the total flux. And so the field is only half that strength. Okay, so when I am looking at the whole sheet, my electric field is going to be my charge density divided by the electric constant. And when I'm only looking at the top or the bottom, it's going to be the charge density divided by half, divided by the electric constant. Okay, so this is for a plane, infinite sheet. And the reason that you need an infinite sheet, or at least can approximate your situation as an infinite sheet, is if this is not an infinite sheet, then at the edges, your field lines start to do funky things and they start to bend and bow out. And the bottom electric field lines would do too. So near the edges, we would get what we call fringe effects, right? And Gauss's law, when you do the symmetric calculations, those fringe effects make things really, really difficult. So that's another reason why we try to focus on the infinite cases or the really highly symmetric cases. We don't like those fringe effects. Okay, one of the most important examples is going to be the uniformly charged sphere. Ooh. Okay, the uniformly charged sphere. And the uniformly charged sphere has to be an insulating sphere. It must be an insulating sphere. Okay? So you basically take insulating material, dump charge throughout, and try to make it as uniform as possible. And it must be insulating because if it weren't, if your charged sphere were not insulating and were conductive, then what would happen is the forces on your charges would not be symmetric except at the center and at the edges. And when you get down into the realm of individual charges, it's highly improbable that any charges collecting at the center would actually feel a truly uniform force on all sides. And so it'd be really highly unlikely that the charges at the center would not feel a net force either. So if your material were conducting, your charges would feel these non-zero electric repulsive forces from each other, and it would cause them to move and scatter. And so the result is, if you have a conductor, your charges, the equilibrium situation for conducting surfaces, or volumes, I really should say, the equilibrium situation for conducting volumes is for all the charges to get as far away from every other charge as possible until they're so distributed evenly that the net force on any given charge is zero, and that only happens when they've all collected at the surface. So for a conducting material, your charges are going to collect along the surface, and this is a universal result. This is why things like Faraday cages work, why your car is an electrically safe place during a lightning storm and things like that. It's not so much that your car is grounded with the tires, it's that the electric charge travels along the surface of your car and doesn't penetrate in. or else it would not be in a good state to then achieve static equilibrium, which is what charges want to do. They either want to achieve static equilibrium or go into the ground. So your car is safe because of the metal casing, at least electrically. So you have to have insulating material, and if you have insulating material, right, you have insulating material, and you have a uniformly charged sphere with charge density rho. Okay, which is equal to charge per unit volume. Okay, so there's two cases. The first case, what is the field inside the sphere? And then number two, what is the field outside the sphere? So inside, we draw a Gaussian surface, and because this is a sphere, we'll draw a spherical symmetry. And we will say that our large, the actually charged object, it has a radius of r. And we will say that our Gaussian surface has a radius of little r. Okay? So, what is the electric field inside the sphere? What does it look like? Right? Well, inside the sphere, we still have E is equal to, or I'm sorry, integral of E dot dA is equal to Q enclosed over epsilon naught. And E dot dA, right, because we're arguing that the Gaussian surface is centered on the center of the sphere, it should make sense that however the field behaves, the field is going to be uniform across this surface. And because that field is going to be uniform, the electric field comes out of the integral. And so, E being uniform coming out of the integral, dA equals Q enclosed over epsilon naught. Okay, so what is Q enclosed? So this is going to take just a little work, but bear with me, right? So let's let the total charge on the sphere be capital Q. Okay, the total charge on my sphere is going to be capital Q. The volume of my charged object is going to be 4/3 pi r cubed. So rho is going to equal Q over 4/3 pi r cubed. Okay? Rho is going to equal Q over 4/3 pi r cubed. But my Gaussian sphere is going to contain a fraction of that, but with the same charge density. So the charge density rho can also be thought of as the amount of charge enclosed by the Gaussian surface divided by the volume of that surface. And it has volume 4/3 pi little r cubed. So Rho is going to equal Q enclosed divided by 4/3 pi little r cubed. And the charge density is constant, so both of these rows are equal. So what I can do is set both of these equal to each other and solve for Q enclosed. And 4/3 pi pi. So Q enclosed is going to equal Q, capital Q, times the ratio of r cubed to capital R cubed. So the larger I make my Gaussian sphere, if I expand outward toward the surface, I enclose more charge, and this ratio gets much closer to 1, and my total enclosed charge approaches the total charge capital Q. So I can plug this into my equation, and remember, dA is over your Gaussian surface. So this is going to be, if I go ahead and say, okay, the integral of dA is just A, what is A? It is 4 pi r squared. Remember, the surface area is 4 pi r squared, but it's over the Gaussian surface, so little r is my radius. And this is going to be equal to Q r cubed over r cubed times epsilon naught. And maybe we should write it like epsilon naught over r cubed. And that kind of keeps this ratio in sight. Okay. And so solve for E, and you get Q r cubed over 4 pi epsilon naught times little r squared times capital R cubed. But little r squared and little r cubed cancel to the point where I'm just left with an r. And so my end result is Q over 4 pi epsilon naught r cubed times r. And I've written it this way to stress the fact that this quantity is constant. My total charge is constant, and then everything else in the bottom is constant, and only r is my variable. So this is a linear function. At the very center where r is 0, if little r is 0, then E is 0. But then it grows linearly with slope Q over 4 pi epsilon naught capital R cubed. It grows with that slope until it reaches, and by the way, if this is on this axis is R and this axis is E. So my E field grows linearly with R until it reaches the surface. So then what happens when it is at the surface, or beyond the surface, actually? What happens beyond the surface? So let's redraw my sphere. Has radius capital R, total charge capital Q, and I draw my Gaussian surface to enclose the whole thing now. So now we're outside the sphere. And if my Gaussian surface is suitably situated, then the electric field coming off of the charged object is going to be uniform and is going to pierce the Gaussian surface with the same value everywhere. And again, that's the symmetry that we're looking for. And if that condition is met, then E comes out of the integral, and it's just dA. But Q enclosed now is the total amount of charge. And so if my Gaussian surface has a radius little r, then I've got E 4 pi r squared equals Q epsilon naught. And E is going to equal Q over 4 pi epsilon naught r squared, which is the same thing as KE Q over r squared, which is the field of a point charge. Okay, the field of a point charge. And so any spherically symmetric charge distribution, when you're outside that charge, is going to give you the value of your point charge, or the value of a point charge located at the center of that object. Okay? So if you think of all of that charge Q condensed down to the center of the charged sphere and of the Gaussian sphere, then these two electric fields give us the same exact result. A point charge and that same amount of charge smeared over a spherical surface give us the same value of the electric field. Okay? Now, here's a point to drive home. So outside the sphere, okay, well, inside the sphere, if this is R and this is E, as a function of R, E grows linearly inside, then it hits the sphere, and outside it dies off 1 over R squared. So what happens right here at the boundary? Okay, well, ideally, this formula and this formula should match. Okay, because E in, if we label this E in for inside the sphere, and this is E out, E in and E out should equal each other at the point where my Gaussian surface equals the surface of the charged object. Is that true? So if I plug in capital R for little r into my E in expression, this reduces to Q 4 pi epsilon naught r squared. Okay? And E out does the same thing, because I'm substituting capital R for little r, and so then this is just going to be 1 over 4 pi epsilon naught, which is K, right? Q over now capital R squared. And so the expressions agree. So it's at the surface here. It's at the point R that my inverse square law behavior then comes in and takes over. Okay? So it's at that specific point that comes in and takes over. Okay? So I hope you find these helpful, and if you still need help, don't hesitate to ask, and we will see you in the next lecture where we will start capacitance.